So sections 5.1 and 5.2 are both going to be dealing with complex number system, and we're going to have sort of an introduction to what this looks like in 5.1 and then go just a little bit deeper in 5.2. So our title is Complex Numbers, and our leading idea is the following. Complex numbers combine real and imaginary parts, two different dimensions that work together to create something meaningful. At first, imaginary numbers may seem strange or hard to believe, but they're essential to understanding many real-world phenomena. Faith in God is similar. Sometimes we face things beyond what we can see or fully understand, imaginary parts of life that challenge our logic. But just as complex numbers reveal deeper truths when combined properly, faith helps us trust God's unseen work in our lives, knowing He is always present and powerful, even when we do not fully grasp it. So one of the things that's mentioned in here that I want to sort of put to bed right away is that imaginary doesn't mean they don't exist. It's a terrible word, just absolutely terrible. But it is more like this is describing it's another dimension, okay? So, I don't know, think like you're in something with Marvel. You're in another dimension, okay? That's what we're doing. We're doing something in a different dimension, and this dimension they've labeled as imaginary numbers, okay? So we're going to start out with what an imaginary unit is. This undoubtedly you have seen before. An imaginary unit I is defined as the square root of -1. So somewhere along the way, initially people talked about the fact that square roots can't have negatives underneath them, and that's true, but only if you're working in the real number system. That's one dimension, right? When we broaden our description to the complex number system, which includes imaginary values, the square root of a negative number has a name, and it's called I. The other way you can describe it is that the I squared value is equal to -1. So those are two sort of descriptions that are used in tandem, and you can think about them either way. Complex numbers then combine these imaginary units, these I values in this one dimension, with our real number system as well. So we get numbers that look like A plus BI. And the cool thing about imaginary numbers is it works so much like algebra, you're going to feel like, did I already do this back in high school? I just didn't have I's, I had X's everywhere. So a lot of what you're going to do is going to feel very much like what you've seen before. And depending on what your history in mathematics has been or what the curriculum sort of involved, you may have seen these actually done. A lot of this done in an Algebra 2 kind of course in high school. It just depends on where your curriculum sort of went. But it's often covered at that point or in a pre-calculus kind of course if you took something like that in high school. So adding and subtracting complex numbers works, again, just like algebra does. Things that are real get combined. So a real number and a real number are able to be combined. And imaginary values are able to be combined. So if they have I's, they can be combined, just like if they had single X's, okay? So we're going to add and subtract the real parts. We're going to add and subtract the imaginary parts. And it's going to look just like what you would expect it to do. So if we have the number -2 plus 6i, and we have the number 4 minus i, what that means is that we're going to add the imaginary parts and add the real parts. Standard form puts the real number parts first, okay? So my math lab might force that to be the case, and if you flip it, they might tell you something wrong. If you flip it for me, I don't care. It's not that big of a deal. I just want you to sort of be aware of that possible thing that my math lab might do. So we're going to do this sort of in the standard order. So we have -2, we have +4, so those add together to be 4. And then we have 6i and -i, those add together to be 5i. Nod your head if that looks okay. Did I do something wrong? Oh, I wrote 4. I meant to write 2. I'm sorry. Thank you. 2 and then 5i. Okay, aside from that, does that look okay? Yeah. Okay. Now, you might say, okay, we just did something with i's back in section 4, in chapter 4, right? We did. This I is not the I, component of a vector form. So especially when we get to this test, you really, really, really need to be careful that if you're talking about vectors, they have the vector hats. And if you're talking about imaginary units, they don't, because they're not vectors, okay? So these are i's, they don't have anything on top of them. So this is 2 plus 5i. If we're doing subtraction, same idea. What do you think you're going to do with a negative outside the parentheses? You're going to distribute it, you bet. So this negative in there is going to distribute through, and this negative here is going to distribute through. So the first thing I'm going to do is simply distribute all the negatives, and then I'm going to combine like terms, okay? So I have a 7 at the beginning, and then I have the opposite of -9, so this would be +9. And then I have the opposite of 2i, so it'd be -2i. Then I have the opposite of 17, so that's +17. And then the opposite of -i is +i. All right, is that okay? Okay, so we're going to find all the real parts. So we've got 7, 9, and 17. What does that give me? 33. And then we have 2i, negative 2i rather, and I. So that gives me negative I. So 33 minus I. Okay, any questions on that? All looking good? Okay. There is a caveat when it comes to multiplication, okay? So it works the same way. There's just sort of an extra step on the end of it. So when we're multiplying with complex numbers, we do it just like we did with polynomials in algebra. But we have to remember at the end that if we have an I squared, we can't leave it as I squared because I squared has a value. I squared is equal to negative 1. So any I squareds that show up get replaced with the value negative 1, and then you simplify further if there's another piece that can be combined with it. Okay? And it says simplifying powers of I accordingly. So let me show you what that means. If you had I cubed, for example, you can't have that left either because I cubed is the same thing as I squared times I, right? Powers of exponents. And I squared is negative 1, so this is negative I. So anytime we have powers of I, there's going to be a way to simplify them. They might simplify to 1s or negative 1s, or they might simplify to i's or negative i's, but those are the only 4 choices, and we simply break them down with powers of exponents to find out what they do. Your book does not do, at least I don't remember it doing, you can tell me if I'm wrong later, does not do lots of big powers of I. I have used algebra and pre-calculus books before where there's an entire sort of section of things where it's like, what is I to the 97th? Okay, well, we can break it down. That's fine. We just need to break it down and figure out how many 2's and things are in there. You know, we can do all of that. Your book doesn't seem to focus on that. So the numbers we're going to be dealing with are going to be small powers of I. Things that come about simply by multiplying, typically speaking, okay? So we're going to get things like I cubed. If we had I to the 4th, let me mention it right now, just because it's so nice. It's I squared and I squared. And what are each of these I squareds? Negative 1. And what happens when you multiply negative 1 and negative 1? You get positive 1. So the only thing that can happen when there's powers of I is to either still have I, for it to change to negative I, for it to change to negative 1, or for it to change to positive 1. Those are the only 4 things that will happen. And our values will be small. Mostly speaking, I think they'll stay between powers of 4 and down. But if they get a little bit bigger, we'll look at it again. Okay, so let's take a look at what this means in terms of actually doing a multiplication. So we're going to distribute just like we would with polynomials, right? Just like in algebra, we're going to distribute through. So negative 8i times 2i would be negative 16i squared, right? Great. And then negative 8i and negative 7 multiplied would be positive 56i. Okay, is everybody good? All the pieces looking okay? So in algebra, we would stop here. There'd be nothing else to do. But I squared has a different value. No powers of I will be left at the end. Its value is negative 1. So I'm going to write it in this time. Next time, maybe we won't, but I'm going to want to be very clear what's happening here. That I squared is being replaced with negative 1. So that negative 16 will become a positive 16. And the 56i at the end remains. Is that okay? All right. What if you have a binomial times a binomial? You distribute, right? You might have used the acronym FOIL, right? First, outer, inner, last. So I'm going to do 8 times negative 3. That's going to give me negative 24. 8 times 9i is going to give me 72i. Negative 4i and negative 3 would be positive 12i. And then negative 4i and positive 9i would be negative 36i squared. Did I get all those pieces correct? Okay. Some of them combine, right? The ones in the middle often combine, and they do in this particular case. So I have negative 24 at the beginning. I have, it looks like 84i. Is that right? And then in the same step, I'm going to go ahead and write down that I know that I squared is negative 1. Y'all good with that? Okay? So that means that at the end, instead of it being a negative 36 with the i's on there, I'm going to end up with a positive 36. And then these will combine. So what is negative 24 and positive 36? 12. So 12 plus 84i would be standard notation. Real first, imaginary second in standard notation. Now, do you have to show every single step? No. If you can combine some of those steps, feel free to do it. Your algebra skills are good to do that with. Go for it. That's fine. I just want to make sure everybody sees where all the pieces are coming from and also specifically sees those I squareds turning into negative ones. Okay, is everybody good? Okay. Now, we have talked about conjugates before. We've looked at rationalizing denominators. Nod your head if rationalizing denominators sounds like a familiar statement. It should, right? We don't leave square roots in the bottom, right? Well, the same sort of thing happens when we're working with division and imaginary units. We don't leave an imaginary unit in the bottom either. Okay, we always want to have a rational number on bottom, and an imaginary unit is not rational. It's imaginary or complex. So we're going to use conjugates in this case as well. So if we have a conjugate of a plus I, it's a minus I, or a plus bi written here, a minus bi. So it's the same thing we saw before when we were doing with radicals. So when we had something like 1 over the square root of 3 plus 1, right? The way that we eliminated that denominator having a radical is that we multiplied by this. Do y'all remember that? Same things, opposite sign in the middle. If we do it to the bottom, we have to do it to the top. We're doing the exact same thing here. It's just that we're doing it with i's involved instead of square roots involved. Okay? So we're going to be working with conjugates. And they come about in the same place that they do when we're working in our rationals, right? Rationals versus irrationals. They come up with when we were doing something like this. There's division involved. There's a fraction. So we have something that has an imaginary unit on bottom, in this case 4 plus I, and we multiply it by the complex conjugate. So what is the conjugate of 4 plus I? 4 minus I, you bet. And anytime we're working with fractions, whatever we do on bottom, we have to do on top, right? Okay. Now, the denominator is going to have some nice features that show up by doing this, but let's actually multiply this one out completely so you can see it happen, and then we'll look at how we could shortcut it if we wanted to the next time around, okay? Now, the numerator, there's no shortcutting. We're just going to have to multiply that out. So I'm going to multiply my 3 through here and distribute. So I have 12 and minus 3i. Good on top? Okay. The denominator on bottom, right, we're going to multiply this out, distribute, or FOIL. So the first ones are going to be 16. The outer, 4 times negative I would be negative 4i. The inner, I times 4 would be 4i. And the last, right here, would be the I and the negative I, which would be negative I squared. And that's what it looks like. Now, of course, the reason this happens and this works is because these inner and these outer terms in the middle there, negative 4i, positive 4i, always add to 0, right? That's what we did to do that. I mean, like choosing conjugates purposefully does that. And again, it pushes back into differences of squares in algebra, right? That's what the differences of squares do. When you have something that looks like x squared minus 81, you can factor it because x squared is a perfect square and 81 is a perfect square. And so they have this beautiful factoring that allows you to do something like this. Nod your head. One of them should be plus. Nod your head if that looks familiar. That should look familiar, okay? We've talked about it this semester even. Okay, so this is how we're actually using these complex conjugates, is in the same form. So as mentioned, these are going to add to 0, right? And the part at the end, negative I squared, is going to become a real number, right? Negative I squared would be plus I, or plus 1, excuse me. So this negative here, and then I squared is negative 1, so we end up with positive 1 at the end. So I have 12 minus 3i, and I have 16, and then it's plus 1. And the middle terms cancel. The last term becomes positive 1, so we have 17 on bottom. So 12 minus 3i over 17. Now that's not standard form. Standard form is supposed to have the real number part at the beginning and the imaginary part at the end. Right now you have both of those pieces over a single denominator. So we're going to separate it into 2 fractions. So this looks like 12 over 17 and negative 3 over 17i. And if either of these fractions could be simplified, we would. But 17's prime, so we're not going to be able to do that. Now, would you like to see a shortcut if you'd like to use it for that denominator, so we don't have to multiply it out FOIL every time? The whole purpose in what we're doing when we're doing this is that we're going to get the first term squared. That'll be 16. We're going to get the last term squared. That's I squared. And it's going to change the sign that's there. So we're going to end up with a positive 1, right? Because it's going to be negative when it multiplies by itself. Right? This negative and this positive are going to multiply. And then they're going to end up changing that sign. So it's always going to end up being the last term added, squared. Okay, so we're going to get 16 plus 1 on the denominator. So if I use that same idea for this denominator, let's just check it out so you can see what it looks like. You'd square that first term. So what's 2 squared? 4. And then there will be addition, and we're going to square the last term. What is 3i squared? Square, not multiply, square. 3 squared is? 9, thank you. And then the I squareds are going to make it to be a positive when we're done. We're going to get a denominator of 13 here. Okay? I'm going to multiply it out to show you that it really worked, but that is going to be what we're going to get. We're going to get a 13 on the bottom when we do this. Now, what is the complex conjugate again? Because I got to do it on top no matter what. I don't have a shortcut on that. Yeah, it's 2 minus 3i. So what I'm actually doing then is 2 minus 3i on top and 2 minus 3i on bottom. Now, the denominator is the part that's going to collapse nicely. The numerator is not going to. So it'll have some collapsing, but not as nice. Let's say it that way. So if I do first, outer, inner, last on the denominator, I've got 4. The outer is minus, 6i. The inner is plus 6i. And at the end, I have minus 9i squared. Okay, that's the denominator. The numerator, the not so nice one, or at least not so standard kind of one. So I multiply the first terms together. That's going to give me 6. I'm going to multiply my outer terms together. So 3 times negative 3i gives me negative 9i. We'll do our inner terms, negative 4i and 2, negative 8i. And then our last terms, negative 4i and negative 3i. Yeah, so it's plus 12i squared. Is everybody okay? Okay, so I'm going to combine i's on top and bottom, and I'm going to replace I squareds at the same time. If you need to see it in 2 steps, do it in 2 steps. So on the top I have 6, and then I have minus 17i, and then I have plus 12 times negative 1. That's going to be negative 12 at the end, right? On bottom, I have 4. These two add to 0, and then I have minus 9 times negative 1 at the end. There's that plus 9. All right, so my numerator has a negative 12 here. So I have 6 minus 12, or negative 6, and then minus the 17i. And on the bottom, as predicted, I get 13. How are we doing? Doing okay? And then what's my last step? Splitting them. Davin, do you have a question? Because I want to answer it if you do.
Where did the negative 12 go again? I'm sorry.
I combined it with the 6 at the beginning. Yes. Any other pieces to clarify? Okay. And then just as Cameron said, we're going to split this. So I'm going to have negative 6 over 13 and then minus 17 over 13i. And nothing simplifies. Some will, but these simply just don't. Okay, what do we think? It's like algebra with a twist, yeah.
Couldn't you also write it as like the whole fraction, negative 6 over 13 plus 17 over 13i?
Okay, say that again. I'll write down what you're saying.
So negative 6 over 13, that's the whole fraction, plus 17 over 13i, would that be the wrong form?
Like that?
Yeah.
I think what you're asking about is this negative, right? Where this negative should be?
Mm-hmm.
So we need to have both of them present. If I wanted to pull the negative out like you're suggesting, it would have to look like this. with a negative on both of them because the negative's still on both pieces.
Gotcha.
And we want to have it sort of distributed out in format instead of compacted with a factored format. So we won't want to leave it written that way. But it would be correct, just not in completed form. Okay? All right. So principal square root is something you've seen before, but maybe not heard it called this. And in fact, it wasn't too long ago that I got a phone call from a local private school asking a question about this. And the teachers who were working there with students who have degrees in mathematics had forgotten this important piece. Okay, so this is not something that people always remember, okay? And I was able to clarify and help them to remember, and they're like, oh, right, I forgot about that, okay? So this is called a principal square root. So for any positive real number b, the principal square root of the number negative b is defined by the square root of negative b equals I square root of b. So what they're talking about here is the fact that if you have a square root in a problem already, you don't have to do anything. But do you remember somewhere along the way that if you insert a square root, you have to put a plus or a minus? Do y'all remember that? So what was happening in that particular situation is that the teacher was wanting to put the plus or the minus every time with the square root. But that's not what that means. If you have, I'll use a real number for a moment. If you have square root of 4 asked of you, it is asking you what the principal square root is. In other words, what is the positive answer of this? And it's 2, right? Now, if you had the problem set up like this, where you put the square root on, then there are actually 2 values, positive 2 and negative 2. But when the square root is in the problem already, this is called a principal square root, and it means I just want the positive part. And that's what you see happening here. So there's a negative b, that's fine. And when you put the negative b underneath here, then that negative that's underneath there separates. So you have the square root of negative 1 times b. The square root of negative 1 and the square root of b looks like this, and we identified that the square root of negative 1 is I. So this is what it becomes. And notice no pluses or minuses show up. Okay, no pluses or minuses show up because we didn't put the square root on. It was there already. So that's what that means when it talks about principal square root. So let's see a couple of these. I think we have time for all 3 of my examples on this set before we stop. Negative 64, square root. Well, the negative part becomes an I, right? Okay, so a negative underneath the radical pulls out of the radical as an I. What's the square root of 64?
8.
It is 8. And we usually write the 8 in front of the I. Okay, if you wanted to write I times 8, you could, but that's a little awkward. 8I. Okay, everybody good? Not terribly crazy, but notice no pluses or minuses, right? We're not going to see them showing up when we start out with square roots. Here's one, square root of 200. This one's not a perfect value. 64 was perfect square. It was great. This one's not. So I want to break it down into a few things. Let's break it down like this first. Okay? Square root of negative 1 is I. Okay, cool. 200. We've broken down square roots before, but it's been a minute, so let's double check on that. If you can divide it, you can, and you will. What will 200 divide by? Somebody give me something. 20 and 10. That'll be fabulous. Neither of those are primes, so they can keep going. What will they divide by? Okay, 2 and 10 for the 20, that'd be fine.
5 and 2.
And then 5 and 2 here, and then this 10 would also be a 5 and 2. So if you're using a factor tree, which is pretty common, be careful that you get at the end all the ends there. So there's a 2, a 5, a 2, a 5, a 2. There's lots of them, okay? Don't lose one of them. So what we're looking for, if we're looking for things to come out of square roots, so we already have the I coming out, is we're looking for perfect pairs. So this is a pair, right? There are 2 2s. So I can pull a 2 out. There are also 2 5s. So I can pull a 5 out. And then the loner stays there, right where he was before. You only get to come out of a square root if you're in a pair, okay? And then if you take a look, this will give you a 10 at the beginning, I square root of 2. Now, that's not standard notation. I would encourage you to write it that way, and I think my math lab will be just fine with it. But let me show you what standard notation really looks like here. It looks like 10 square root of 2 and then I at the end. That's standard notation. The problem with putting the I at the end is that at some point, you're probably going to be moving quickly enough, or maybe you write messy anyway, and it's going to look like the I's underneath the radical, and it's not. We don't want it to look like it's under the radical, which means this is a safer way to write it. Make sense? Okay, one more example and we'll end for today. This one has something that's got subtraction. You can't do anything to pull it out if there's subtraction except to clean it all up and to do the subtraction first. So do not be tempted to say, hey, I've got a 5 squared, that 5's coming out. No, it's not. You got to do everything underneath there to clean it up first. So if we clean this up, this is 25. And I'll save you the step of multiplying it. This is minus 72. Okay? And if you subtract them, you get negative 47. Okay? So you got to do all of the stuff underneath first. The negative comes out as an I. But 47 is prime. It does not break down anything, so it just stays underneath there as is. So do not be tempted to see something squared and pull it out. If there's addition or subtraction, you've got to deal with that first.